In this problem, we have a box of books with gravitational force of 325 newtons and moves at a constant velocity across the floor when it is pushed with a force of 425 newtons exerted downward at an angle of 35.2 degrees below the horizontal. We're supposed to find the coefficient of kinetic friction between the box and the floor. So again, we see that it is a constant velocity, so therefore it is an equilibrium problem. In this case, we're given the gravitational force, not the mass. So that makes things a little easier for us. But we notice that we are not just left, right, up, and down forces. We have an applied force downward at an angle. So in this problem, we're going to look into how to do one of those types of equilibrium problems. We start this first the same way as we did before. We draw our free body diagram. We have a gravitational force, which is down, because we're on the earth. We're on a surface, so we have a normal force, which is up, perpendicular to the surface. We are pushing it slightly to the right, so that means that there is friction to the left, parallel to the surface. It is moving, so it is kinetic friction, not static friction. And then we have this applied force. Now this applied force here is not just to the right, but down at 35.2 degrees. So we have our free body diagram. Now we write down our givens. And we are given that the gravitational force is 325 newtons. We're also given that the applied force is 425 newtons. And we want to find out what is the coefficient of kinetic friction between the floor and the stack of books. First thing we do, whenever we have a force that is at an angle, so we already have the gravitational force, we don't have to calculate that. But if we have a force at an angle, we're going to break it into its two components. The component that is parallel to the surface and the component that is perpendicular to the surface. I'm not going to call it x and y because we're going to find the total in the x and the total in the y. We don't want to use that same letter. So we'll find the force parallel to the surface and the force perpendicular to the surface. Now to find the force parallel to the surface, we're going to use our trig. That is the adjacent side, so that is cosine. So I'll write this stuff up here. So to get that parallel component, it is the applied force, 425, times the cosine of 35.2 degrees. And we get the parallel component comes out to be 347.3. And that would be newtons. Then we get the perpendicular component. That is the opposite side of our triangle, so that is the sine. So it is our hypotenuse, 425, times the sine of 35.2 degrees. And we get that perpendicular component to be 245 newtons. Now what we want to do is we want to find that coefficient of kinetic friction. So if you go to our equations, there is only one equation with coefficient of kinetic friction. There it is. So that is our one and only option. However, we do not know the kinetic friction, nor do we know the normal force. So we're going to have to go to our conditions of equilibrium, again, constant velocity. Go to our conditions of equilibrium. The total force in the x direction is 0. And the total force in the y direction is 0. To get those two forces, in order to get our coefficient of kinetic friction. Well, what happens, what transpires here, is we are replacing this applied force with its two components. So we're never going to use that applied force again. Instead, we have its two components. We just ignore that from now on. Okay, we'll never use that again. So in the x direction, we have two forces, the kinetic friction and the parallel force. So we go back here, we have the kinetic friction plus the parallel force is equal to 0. Well, we want to put in our positive negatives. Kinetic friction is to the left, so that's negative. And parallel force is to the right, so that's positive. We know the parallel force, so we're now going to solve for the kinetic friction. Parallel force was 347.3 newtons, and so the kinetic friction is also 347.3 newtons. So now we have our kinetic friction. We're halfway there. We just need that normal force. So we go to our condition of equilibrium in the y direction. In the y direction, we have the normal force up, the perpendicular force down, and the gravitational force down. Remember, we just scribble out that applied force. We don't use it at all, ever again. So after we get the parallel and perpendicular components, you don't use that force anymore. So we have three forces in the y direction. That's how this is a little different. We have the normal force, we have the perpendicular component, and we have the gravitational force, and they equal 0. Well, let's consider positives and negatives. Normal force is up, that's positive. Perpendicular component's down, that's negative. And gravitational force is down, that's also negative. So now, we can put in our values. Perpendicular component is 245, and gravitational force is 325. So we solve for the normal force, and we get that the normal force is 570 newtons. It is not the same as the gravitational force. And that's what a lot of people unfortunately want to do. They always want to make the normal force the same as gravitation, but very seldom is the gravitational force and normal force the same. So in this case, because we are pushing down, the normal force is going to be more than the gravitational. So we have the normal force, we have the kinetic friction, which is 347.3 newtons. That's equal to our coefficient times the normal force, which is 570. Solve for our coefficient, and the coefficient turns out to be 0.61. There are no units for coefficient.